All right, we're back. We're on page 2 of notes 11. We are integrating powers of trig functions, and we've seen that a like pretty powerful technique, like maybe the technique, is you kind of like look for du, which is weird. So like you're basically looking for u, but the key is you need du to work. And so when you guess, which basically is what you're doing, when you guess what u is, make sure du works, because if du doesn't work, then it's a failed attempt. So let's see if we can do these. It says to like test them in your head, which like I do think you should do. But like, how are we going to know that we tested it in our head if I don't like write it out here? So I'm going to write it out. In this problem, there's a tangent and there's a secant. I mean, there's a tangent cubed and a secant cubed. So I'm thinking that like either u is going to be tangent or u is going to be secant. So what I would do is I would test it. So I'm thinking this, right? So if u is equal to tan of x, then du would have to be secant squared of x dx. If now this is the key thing. If du is secant squared of x dx, that's going to leave, that leaves secant of x, right? Because it's secant cubed. So it leaves a secant of x, and I cannot really turn this into tangent. So this is a problem. So I would abandon this at this point. So this is what I would think. That would be my first thought. If u is equal to tangent, then du is secant squared. It leaves me with a secant, and I can't turn that into tangents. So this isn't really a good way to go. So then I would switch over, and I would say, well, what if u is equal to secant of x, right? I mean, it's really the only other choice. Then du is secant x tan x dx. Okay, so since there's a tan cubed, this is going to leave, since there's a tan cubed, and I'm saving one of the tangents. I'm also saving one of the secants, which kind of screwed me over on a previous problem, so I'm going to actually like do some work on this. It leaves me with tan squared, which can turn in turn to Rn. I can turn that into secant squared. So we're good to go. So that's the method that we're going to use. So that's it. You like make your choices. The more problems that you do, the faster you get. And you just like make choices. So here's what we're doing. We're separating our original integral into tan squared, secant squared, and then secant x, tan x, dx. We're saving this. This is what we're saving. Now, once we've decided what to save, turn everything else into the thing it needs to be, right? So u is equal to secant. I need to turn all my tangents into secants. But I can do that because tangent squared is secant squared minus 1. So I get secant squared minus 1, secant squared, and then secant tan. Sometimes people try to invent a function called sectan, which does not exist. We're saving this. All right, u substitution at this point, I think, is the way to go. So this is u squared minus 1, u squared du. So that's u to the 4th minus u squared du. So I'm going to integrate and sub at the same time. 1/5 secant to the 5th minus 1/3 secant cubed plus c. There you go. So test it out. I mean, that's like, and I think that's what people don't like about these is that like everybody always just wants like literally everybody, including people who know how to do the more challenging way, but correct way. It's like everybody just wants it to work, but it doesn't necessarily work. So you gotta like do some, gotta put some effort in. All right. This problem is probably going to illustrate why you usually don't do definite integrals with this, because at the end you got to evaluate all these trig functions, but let's see if we can do it. So I'm not seeing a lot of options here. I mean, I can turn tan cubed into tan squared times tangent and like hope for the best. So that's what I'm going to do. 0 to pi over 4. I got tan squared, which I can change into like secant things, and then tangent, which I guess I'm saving. So this will be 0 to pi over 4 So tan squared is secant squared minus 1, and then tangent dx. And then if you don't see where you're going, you just keep expanding. So I'm going to expand this into two separate integrals. So secant squared tan, and then minus tangent dx. I didn't want to write the integral twice. All right. Choices. This integral, actually, you could make u equal tangent. And then if u is equal to tangent, the derivative of tangent is secant squared. So it's 1/2 tan squared. That's totally fine. Or the derivative of secant is secant tan. So you can make it secant tan, and then integrate that to get 1/2 secant squared. Like, you could go in either direction. Which of them would I rather mess with? I'd rather mess with tangents, because tangents are, like, I have more of those memorized. So I'm going to go with u is equal to tangent. So u is tangent. Maybe I'll use a different color, because I've been highlighting du's with that. I'm going to make u equal tangent. Derivative of tangent is secant squared. So this is perfect. This is 1/2 tan squared of x. And you know what? Let's just go 0 to pi over 4. And then we also have to integrate from 0 to pi over 4. Tangent, which you may remember, you may not. I always change it into sine over cosine. An alternative method is to multiply by secant over secant. If that makes sense to you, like, go for it. So this, I'm doing like 2 problems at the same time now. The tangent of pi over 4 is 1, 1 squared is 1. The tangent of 0 is 0, 0 squared is 0. Here, minus. Okay, so if I make u, obviously you make u cosine. So then du is negative sine, so actually this can just be plus the natural log of the absolute value of cosine. Not plus c, we're going 0 to pi over 4. Ugh. Okay, so 1/2 for sure, plus. Yeah, the natural log of the cosine of pi over 4 is root 2 over 2. It's not that I don't know that, it's that where is this headed? And then the natural log of the cosine of 0 is 1. Cosine of 1, the natural log of 1 is 0. So this is 1/2 plus the natural log of root 2 over 2. Well, that's crazy. I think we should check that. And I'm going to be very, very sad when it's not right. Which, like, I think it's right. Integral of tangent of x cubed x 0 to pi over 4. What are these equivalent? I think they are equivalent. Oh man. All right, here we go. I'm gonna write that down just so that you know what the calculator said. So the calculator said, I'm gonna write 1 minus natural log of 2 over 2. Like, that would be if I expand that. Can you expand that? Yeah, 1 minus natural log of 2 over 2. All right, back to the notes, and let's mess around with this this natural log situation, because that's where it came from. All right, here we go. So first I'm doing something really weird. Root 2 over 2 is only because you rationalize 1 over root 2. So I'm going to do this. And then I'm going to do properties of logs. So it's the natural log of 1 minus the natural log of root 2. Then the natural log of 1 is 0. Radical 2 is 2 to the 1/2. Exponents become coefficient. Minus 1/2 the natural log of 2, which is 1 minus the natural log of 2 over 2. So it's equivalent. It's just like crazy. You run into that. Natural log, trig functions, antiderivatives. You can have like a million different versions because of all the identities. And then natural logs, you can have a lot of versions because of the properties of logs. So fun when you get to mix those together. All right. So I will be back in the next video to do more, and I will see you there.